All right, you guys, it is time to start our second unit in chemistry, which is periodicity. Traditionally, periodicity means the quality or character of being periodic or the tendency to reoccur at intervals. And so what we want to do is take this word and actually put it in the context of chemistry, since this is chemistry class, and we want to think about what does periodicity mean in chemistry. In chemistry, periodicity is referring to the study of the periodic table of the elements. And so the periodic part of that title implies that there must be an order or a pattern to the periodic table, and in fact there is. So that's what we'll be talking about today. But first I want to take a little bit of a historical approach and talk to you about why we even have a periodic table in the first place. Way back in the day, we did not know about a lot of elements. So by 1700, only 13 elements had even been identified. And so from the period of 1765 to 1775, 5 new elements were discovered. And prior to this time period, there was really no study of chemistry. Everything was really alchemy, which is sort of what's highlighted in this painting that you see on the left. This painting is titled "The Alchemist in Search of the Philosopher's Stone Discovers Phosphorus and Prays for the Successful Conclusion of His Operation, as was the custom of the ancient astrologers." This painting was done by Joseph Wright of Derby, and he was really trying to capture the spirit of alchemy, which was this sort of mystical search for either the philosopher's stone, which was like an elixir of life, or they were trying to turn everything into gold. And it's entertaining to me because the elixir of life, philosopher's stone type of deal usually involved mercury. So it was like, hey, how about you drink some mercury and we'll see if that fixes you? Which it didn't. So, alchemy, not so much of a thing. But in the 18th century, we started to get into a more scientific approach. We started really discovering new elements. And for my history buffs in there, this was right about the time of like the Industrial Revolution and kind of post-Renaissance and all of that business. And so we really had a great opportunity to start making some new discoveries. So at this point, we're like, hey, we got 18 elements. That's a lot of elements. Maybe we should organize these systematically so that we know what's going on with them. So people started working on this problem, and a lot of things were proposed for a long time, different variations, but one guy in particular came up with something pretty nifty, and we use it still today. That guy was Mendeleev or something like that, Russian dude. And in 1869, he published a periodic table of the elements. And he used basically atomic number, even though that wasn't technically known at the time. So he used atomic mass to organize the table. And he also really focused on the properties and behaviors of elements. So what do they react with? What kind of compounds do they form? What kind of state, like solid, liquid, gas, are they in? And so he organized them based on repeating properties. And he additionally arranged them in order of increasing atomic mass, like I said earlier. And so those things kind of started to shape the periodic table that we know and love today. So if we take a look at that periodic table, it looked like this. And at first you're like, this looks nothing like the periodic table, Miss Olson, get a grip. But it actually has a lot of similarities. So if you look, we've got little hydrogen chilling off here by himself. And they didn't know about helium at this time because it's like an invisible, odorless gas that makes your voice squeaky. So they didn't really know about it. But then you can see we've got lithium, which is number 3, and beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminum, silicon, right? So they're going down the table, and they're actually organized very similarly to what we see on the table today. So he was really on to a good thing, Mendeleev was, and one of the things that really suggested that he was on the right track is that this other dude, Julius Lothar Meyer, who was German, developed the same table at the same time, but Mendeleev published first, so Mayer doesn't really get any credit. But if two people are independently solving the same problem and they start coming up with really similar solutions, that's a good sign that we're on the right track. The other thing that Mendeleev did that was cool was he started predicting new elements. He was like, there's a hole in the periodic table, there's going to be an element that weighs about so much, and it's going to have these properties. And everybody totally thought Mendeleev was a crazy Russian guy. Like, they didn't think he was correct, they thought he was a crackpot. And then all of a sudden, they started finding all of the elements he was predicting, and they were like, whoa, that dude was beyond his time. Like, he knew what was up. But by that time he was dead, so he didn't actually get any credit, really. But you know, he was a smart dude. Lots of other people have put together periodic tables, which is, you know, like cool, but they're kind of crazy. So we'll take a look at a couple of them just for funsies. These are two of the craziest ones I've ever seen. And so this guy, Ingo Vladimir Dagobert Hach, decided that a spinning periodic table of death would be awesome. So we've got hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, you know, just spiraling inward forever, which is somewhat spectacular in a horrible way. And so, you know, this is a good thing. You can see that the noble gases line up: helium, neon, argon, krypton, xenon, radon. And so the families that have similar properties line up as well. And we'll talk a little bit more about what that means later. This other table by Crookes also goes by atomic mass and kind of zigzags and lines up families and stuff. And it has some really valuable patterns displayed in it, but ultimately people really found Mendeleev's table to be the most powerful, and so that's what we use today. Periodic table that we see is this top version that's really shortened and squished down, and it has the lanthanides and the actinides. That's 6 and 7, or the f orbitals, pulled out and stuck below the table. And so really what the table should look like is this big long thing on the bottom, but we actually don't put the periodic table like that because it doesn't fit on 8.5 by 11 pieces of paper very well. So we have to put it, kind of squash it down to make it fit on a piece of paper. What we're going to spend some time doing later today is actually labeling the periodic table, because it has different families and a lot of trends that tell us a lot of good information that allow us to do some chemistry. And so that's why I say that the periodic table is your best friend and it tells you all the answers, because it kind of does. So that's where we're headed with this. The periodic table doesn't have to be drawn this way, but a lot of times it is. And what you'll see is that international periodic tables, there's actually a couple of them hung up throughout the room, are shaped in the same way. They just have the symbols and the element names written in the appropriate language for the country. So a little bit of vocab for you guys. If you're talking about the most powerful tool in chemistry, which is of course the periodic table, there are a couple things you need to know. The first one is that a horizontal row, which is sort of like an energy level in our orbitals, is a period. So we call that a period in the periodic table. So that's a row. That's from left to right across. A group or a family is a vertical column of elements in the periodic table. Elements in a group have similar chemical and physical properties. The reason for this is that they all have the same outermost electron type of configuration. So if you think about lithium, sodium, potassium, rubidium, they all have that S1 ending of their orbital, so they all want to give away that electron. So they all behave the same way, which is to explode upon contact with water. You should probably look that up on YouTube because it's amazing. And so they just give away that electron, and they all do that. Something like chlorine, on the other hand, wants to gain an electron, and so does bromine and so does fluorine, because they all have that P5 ending orbital. So they want to have that P6, and so they get an extra electron, and that's really why we see stuff like NaCl, common table salt, because sodium throws away its electron, chlorine snatches it up, and now we've got Cl minus and Na plus, and they've done a little swap, and everybody's happy. So this idea that groups or families have predictable behaviors due to their electron configurations is something that will serve you well in my class. This beautiful looking periodic table is something that is going to help you a lot later on. So your job for part of class today is actually to make the periodic table on your new packet look just like this one. Color the little blocks, make them really pretty, and give them labels with the legend. And by doing that, you're going to help yourself out a lot moving along. So I'm going to briefly describe these different groups. I can't point at them because I can't write on Google Slides, which is dumb, but try to follow along. So this first family, which is bright yellow with the green hydrogen on top, is the alkali metals. Hydrogen is actually a non-metal, but we group it over with the alkali metals because it has that 1s1 electron configuration. And so this first family, the alkali metals, are highly reactive, explosively reactive. Again, look it up on YouTube. It's amazing. And that's because they've got that 1s1 or 2s1 or 3s1 configuration. That's the first family. Second one are the alkaline earth metals, also pretty reactive because they have those 2 electrons, the s2 hanging out, and if they give those away, they look like our orange noble gases, which have that full energy level because they have that p6 configuration. So those orange guys are the noble gases and everybody wants to be like them. They don't react because they have that perfectly filled energy level, and it's hard to take their electrons or make them take more electrons because they already are in a really good place energetically. This bright green middle section are the transition metals, and those are things that we commonly think of as being metals like iron and nickel and copper and zinc and stuff like that. You'll notice on the bottom row, there's a bunch of not colored boxes, and that's because those are some big, fat, unstable elements that we probably made in a lab, and we don't actually know what their properties are like because they are lasting on like a femtosecond time scale. So like really small time scale, so we can't study them. Also, the next little thing is the gray group with aluminum, gallium, indium. Those guys are called like the post-transition metals or the other metals, and those are important because they form a lot of compounds, they act like metals, and they are also, a lot of them are touching the stair-step line, which is the border between the pink metalloids and the gray other metals. So along that stair-step line, those metalloids, the pinkish ones, have properties that sometimes are metallic and sometimes are non-metal, and that's really valuable. Carbon, nitrogen, oxygen, phosphorus, sulfur, and selenium are additional non-metals, and they are really valuable in biology, and so they're kind of the other non-metals or the molecules that make up, or the elements rather, that make up life. Last but not least are our aqua bluish halogens. These guys are fantastic at reacting. They love to steal other elements' electrons so that they can have that perfect noble gas configuration, and that's what's notable about them. On the bottom, the actinides and the lanthanides, those are those f orbitals. They're really big. A lot of them are radioactive, and that's really all you need to know about them. A lot of them are named after people or places, which is kind of nifty also. Additionally, today you're going to color this periodic table. You're going to label it. I'm going to throw some extra labels on there when I get back on Thursday to kind of help you remember some stuff. But the other thing you should do today is you should watch the crash course on periodicity as well, or the periodic table. It's really good. He explains a lot of great stuff, and be good for the sub. I'll see you guys tomorrow. Thank you.